So we have been looking at the operation and the design of the step down or the buck converter. Okay, so in the last class we have seen how to design the buck converter for a given set of specifications, assuming both continuous conduction mode as well as discontinuous conduction mode, and we have seen the waveforms as well. So now we start by looking at how one can step up a given DC voltage to a higher voltage level using a converter circuit. Okay, and the converter that helps you do this operation of stepping up the voltage is what is commonly known as the boost converter. The basic element that lets you boost a given DC voltage is the inductor. So what we have in the boost converter is an input voltage source Vg, which comes in series with an inductor, and then you have a switch A that can be closed to charge this inductor. Okay, and when the switch is open, the inductor will try to continue its current, so we need to have a switch which will conduct in this direction, and then this energy stored in the inductor can be dumped to a capacitor, which will then provide you the voltage, which is a stepped up version of the input voltage. So this capacitor is C, this is your load resistance, and that is the inductance. This switch can be labeled as B. So as usual, as we did in the case of the buck converter, the way to analyze this circuit is to look at the situations in the two modes, one when the switch A is closed and next when the switch A is open and B is closed. So we look at what is the situation and then draw the waveforms and try to use the volt second and amp second principles to obtain the behavior of the circuit. So if you look at the circuit when the switch A is closed, it is simply Vg, the input voltage source, in series with an inductor, and then you have the switch which is closed, so that is like that, and then you have this. So Vg appears simply, it appears across this inductor, and then it causes a current to flow through it, which we will call it as Ia. So this is the situation when the switch A is on, and the time for which the switch A is on, that is called the on time, or we represent it by the duty ratio. So this is the case where 0 less than t less than dTs we can see. Okay, so now we need to also look at the condition when switch A is opened. Okay, so again we have Vg appearing in series with the inductor, and the inductor is carrying a certain current, so this switch is now open. So we need to close the switch B. So this switch is now closed, and you have the capacitor, and here we have the resistor. So again, when the switch A was closed, you also have a second part of the circuit. We have not drawn what happens at the output. So at the output, this B is open, and then you have the capacitor supplying the load resistor. Okay, so that is the situation for the on time, and this is the situation for dTs less than or equal to T less than Ts. So again, this is your L, C and R. You can indicate the polarity of VL like this, and the current through the inductor is IL. So then one can try to draw the waveforms for this converter and analyze the circuit. So let us try to do that. This is the waveform for the switch A, which would be on for a certain duration and off for a certain duration, and that's the way it goes. Now switch B is operated in a complementary fashion. So you have the waveform or the control part for switch B going like that. So this is the on duration for switch A, and this is the on duration for switch B. So what we draw next is the voltage across the inductor. So let us do that here. This is the voltage across the inductor. So when switch A is on, you can see that the voltage across the inductor is simply equal to Vg, that is the voltage appearing here. And when switch A is off, that is when B is on, you have Vg minus the output voltage. So the output voltage is going to appear across the resistor, right? So this is VO. If I call this as VO, then when switch B is conducting, you have the voltage across the inductor as Vg minus VO. So that means here I have a voltage of Vg, and then we have said that this converter is a boost converter. So naturally the output voltage is going to be greater than the input voltage. So Vg minus VO is negative. So we can draw it in the negative portion in this fashion. And then it repeats. Now if this is the voltage across the inductor, we can also draw the current through the inductor. Okay. So the current through the inductor, if we try to draw it, let us assume that the current through the inductor is starting from some point in steady state. So when the voltage across it is positive, the current will increase with a positive slope, and then when the voltage is negative, it will decrease, and at the end of one switching cycle it will come back to the same point of current value from where it started. So this is the value of waveform of ILT, and so that is the way this waveform would appear. Now what can we draw next? Yeah, one can also look at what would be the we could look at the currents through the switches A and B. Okay. So the current through switch A would be equal to the inductor current when the switch A is on, and when switch B is on, the inductor current would be equal to the current through switch B. So if we draw the currents, then this is IA of t. You would have the waveform appearing like so. Okay. So that would be the waveform for the current through switch A. And what we next have is the current through switch B, which you can understand that it would be just the negative part. So we will have it in this fashion. Sorry. This would be the waveform of the current through switch B. Okay. And what we can see is that the switch B, the current through switch B, the average value of this current through switch B is going to be equal to the load current, because switch B comes in series with the parallel combination of C and R, and the average current through the C should be 0 as per amp second balance, and therefore the average value of current through switch B, which I can represent it by some value over here, this is going to be equal to I0, right? So having drawn these waveforms, now let us try to apply volt second balance and see what we get for the converter. So volt second balance. So how do we do that? We look at the voltage across the inductor. So this value is Vg, and this we have seen is Vg minus Vo. Okay, so all these axes are time, and this duration is dTs, and this is 1 minus d times Ts. So we see that the inductor voltage is Vg for the duration dTs. So the volt seconds is Vg into dTs plus Vg minus V naught into 1 minus d times Ts. As per volt second balance principle, this must be equal to 0. And so if we simplify this expression, Ts cancels out, and then you have Vg times d, and here you have Vg times 1 minus d. So this means that Vg minus Vo times 1 minus d is going to be equal to 0, which then gives you the voltage gain of this circuit, Vo by Vg equal to 1 over 1 minus d. And 1 minus d is a value which is always going to be less than 1, because the maximum value of d is 1, and therefore you will find that this value is always going to be greater than 1, and that is your boost operation. You always get an output voltage which is going to be greater than unity. So if you plot this voltage gain in CCM, right, if you plot D versus V naught by Vg, what you get would be a curve like that. Well, this value is the value at D equal to 0, which is 1, and then it goes to infinity at d is equal to 0. So this means that at very small values of d, you have a gain which is close to unity, and at very large values of d, you have a gain which becomes very large and approaches infinity as d approaches unity. So this is the theoretical case. In practice, the gain that is obtainable from this circuit is kind of limited. So we will look at what is the reason for this limitation as we proceed. So what is the next step? We need to look at, or we need to write down expressions for the current ripple in this converter. So what is the current ripple? Delta IL, as usually is done, is the slope in any interval times the time period. So during the first interval, when the switch is on, the voltage is Vg. So the slope of the current is Vg divided by L, and therefore you have delta IL as Vg by L times dTs. And this should also be equal to the slope during the off time multiplied by the off time. So this should also be equal to V0 minus Vg by L times 1 minus d Ts. Right. So what we can now do is we can also apply ampere seconds law, amp seconds principle rather, and try to see what that gives us. So for applying amp second balance, you need to find out what is the capacitor current when the converter is operating. So let us draw that waveform also here. Okay, so let us draw the capacitor current waveform also. This is IC of t. Now, what would be the capacitor current? So this is the current IC of t. And what would be this current when the converter is operating with switch A closed? If you apply the KCL at this node, you will get that this should be equal to negative of the output current. Okay. So if we assume the output voltage to be fixed, then the output current is also fixed. So we can draw this waveform as like this, which this value is minus of I0. And when the switch is A is open, then you see that the capacitor current is the difference between the inductor current and the output current. So if the average inductor current, right, if the average inductor current is taken to be IL, then we can say that this is going to be equal to IL minus IO, right? So you get a waveform which would look something like this. This is this IB shifted down by the average value. So let me draw it as a smaller waveform. So maybe this would then be the way the capacitor current would look like. So this is minus I0 and this is simply IL minus I0. So if we now apply the amp second balance, what we then get is minus I0 times dTs, right, and then we have plus IL minus I0 times 1 minus dTs. This should be equal to 0, and again Ts cancels out, and here you have a minus I0 times d, and if you expand the bracket you get a minus I0 times 1 minus d. So this is basically minus I0 plus IL into 1 minus d equal to 0, which gives you the relation I0 is equal to IL times 1 minus d. Okay, so that is the information that you get by applying the amp second balance principle, or you can also write the relation as IL is equal to I0 by 1 minus d, which you can then cast it in terms of the voltages, because this I0 is V0 by R. So this is V0 by R times 1 minus d, and again you can write V0 as Vg by 1 minus d using the relation obtained for the voltage gain. So this is Vg divided by R times 1 minus d the whole square. Okay. So one can also then look at what is the voltage ripple in the capacitor. So the delta V peak to peak is very straightforward, because now you have a situation where the current through the capacitor is minus I0 during dTs, and that is the portion where the current is negative, right? So either this area or this area should give you the charge that is flowing in and out of the capacitor, and so it is very straightforward in this case to write down delta V peak to peak. It is the magnitude of the current during the on time. If we take delta Q, or the charge that is going to be there, is I0 times dTs, and this charge divided by the capacitance would then give you the peak to peak voltage. Okay. Right. So now again, if we look at this expression for the ripple current, we see that this ripple current is dependent only on the input voltage, duty ratio, switching frequency and the inductance, and it is really independent of what is the load current. So it is again then possible that this converter can go into a discontinuous conduction mode if you increase the load resistance, or in other words, if you decrease the average output current, then it is possible that the waveform of the inductor current, which we have shown like this here, can then shift, and at some point it would touch 0, right? It would reach here, and on further reducing the load current, what would then happen is that this current would become discontinuous, right? So what we now would like to understand is at what point the operation of this converter is going to move from a continuous conduction mode to the discontinuous conduction mode. So this operation is what we typically call the boundary between CCM and DCM. So we have seen this boundary in the case of buck converter also. So now we will look at what is the condition for this boundary operation in the case of the boost converter. So let me again draw that waveform here. The operation of the boost converter at the boundary. So at the boundary, the inductor current waveform would just touch 0. Okay, this is IL of t, and it would just touch 0. This duration would be Ts. So now if you look at it, this peak value of the current is going to be equal to delta IL, and the average value of the current we have already seen, it would go through the midpoint. That average value is IL, the average value of the inductor current, and at this boundary between continuous and discontinuous conduction mode, then we have the relation similar to the buck converter. This operation will happen when IL becomes equal to delta IL by 2, right? That is when the waveform will shift and will just touch 0, and if IL, the average value, is reduced any further, it will go into the discontinuous conduction mode, right? So this is the condition for the boundary. Okay. And therefore, if we now substitute the values, we have delta IL, which is Vg by L into dTs. So delta IL by 2 is then Vg by 2L times dTs, and this should be equal to the average value of inductor current IL, as we have seen, and we have already written down the expression for the average value of inductor current in terms of the input voltage, that is Vg by R times 1 minus d the whole square. So if I equate it here, Vg by R times 1 minus d the whole square, then you see that Vg cancels out, and again you have the terms like 2L, Ts and R, so you can bring it to one side and write it as 2L by RTS should be equal to d times 1 minus d the whole square, right? And this parameter 2L by RTS, as we said in the case of buck converter, this parameter is denoted by the letter K, and it is called the conduction parameter. What this K tells us is about the tendency of this converter to operate in CCM or DCM. If you have a large value of K, then most likely is that the converter would be operating in CCM, and with very small values of K, you will almost always have discontinuous conduction mode. Okay, so the condition for the boundary, then we get it as K is equal to K critical, that is the value of K for boundary operation, and this should be equal to d times 1 minus d the whole square. So like in the case of the buck converter, we can then look at how the critical value of K is going to vary with duty ratio. In the case of buck converter, it was a very simple linear variation because K critical was equal to 1 minus d. Now we have a much more complicated variation of the k critical. So let us then plot it and see what happens. So I have plotted this variation and it looks like this. So on the y-axis you have the k critical, which is d times 1 minus d the whole square, and on the x-axis is your duty ratio d. So this variation shows that it is not a monotonically increasing or decreasing function, rather it is a curve with a peak maximum at some value. So what the curve will tell you is that, suppose that you have now a converter for which the values of L, R and Ts are such that your k value is going to be somewhere here. Okay. What can you now tell about the modes of operation? So clearly this point and this point, if I put it down, then you can say that in this region of operation of D, you have your 2L by RTS, right? So this is 2L by RTS, the value for this converter, and therefore during this region of variation of duty ratio, you have 2L by RTS greater than the k critical. So here you have CCM, and then there you have k critical is higher, or 2L by RTS is smaller for your converter, which means that you will have DCM operation. And again, as the duty ratio increases, right? So here this region would then again be CCM operation. Right? And so if your k now moves up or down, the region of D for CCM or DCM will also correspondingly move up or down. And suppose that your k now has a value which is somewhere here. Okay, this is now your new value of k. So this was k, and let's say this is k dash, your new value of k. This value of k dash is now above the k critical for all values of D, and this means that for any value of duty ratio, if you maintain the constant 2L by RTS to be above this peak value, you can have assured operation in the CCM region. So then we need to find out what is this value above which we can operate in the CCM mode. So how do we do that? We can look at what is the value of D at which this k critical becomes maximum, right? So what we can say is that at the maximum point, dk critical by dk by dd should be equal to 0, and k critical is d times 1 minus d the whole square. So d by dd of this function should be equal to 0. If we expand d times 1 minus d the whole square, then you get d into 1 plus d square minus 2d. Okay, so this is d plus d cube minus 2d squared. So if you take the derivative, you get the expression 1 plus 3d squared minus 4d equal to 0, and you can solve this quadratic equation to find the values of d. So d is minus b, which is 4 plus or minus root of 16 minus 4 into 3 divided by 2a, which is 6. So what you get for this d is two values, that is one is d equal to 1 and 1 by 3 are the solutions. So from the plot itself we can see that d equal to 1, the curve goes to 0, so the maximum value is then going to occur at this point, which corresponds to d equal to 1 by 3. Okay. And what is this critical value of k at that point? That also we can calculate. So k critical at maximum value at d equal to 1 by 3, this can be equal to 1 by 3 into 2 by 3 the whole square, right? So this will give you the value of 4 divided by 27. So that if you do it, it is slightly close to 0.15, and that's where you see you have the maximum. So that is how you can then decide, or you can then design your k value or your inductance, switching frequency and the load resistance in such a manner as to operate in continuous conduction mode. So the similar reasons which we set for the buck converter in order to not operate in DCM mode, or the advantages of CCM mode over DCM for the buck converter, similar reasons apply equally well for the boost converter also. So most of the time when we design the converter, we will try to make sure that the converter is operating in continuous conduction mode. Nevertheless, it would be important to understand the characteristics of this converter in the CCM mode as well, in the DCM mode as well. So let us try to do that also. So what we have now is DCM operation. Right, so in DCM operation, if you draw the waveforms, you have a portion for which the switch is on, so this is the switch A, and a portion for which the switch is off, and so on. And the inductor current in this case will be discontinuous. So when the switch is on, you will have the current which starts to rise from 0 to certain value, and before the off period ends, okay, this is the on time, and before the off period ends for the switch, this current will fall to 0, and then it would remain at 0, and again the cycle would continue. Right, that is the waveform of the inductor current IL of t. Now, what would the voltage across the inductor look like? So the voltage across the inductor, if you try to plot it, when the switch is on, there is no change. You get a voltage of Vg, and when the switch is off, again you have the situation where the switch B conducts. Okay, that means as long as the current is falling, the switch B is conducting, right? So you have a situation where this is Vg minus Vo, and then for the remaining part the switch will remain off, and then the cycle would continue, right? And why does the current go to 0 and then remain at 0? That is only because we have a switch here when we draw the circuit, we drew a switch here which can carry current only in this particular direction, right? That is indicated by this arrow. And we also have a situation where whenever the switch is off and there is a current, this switch would be conducting. So it is easy to say that we can replace the switch B with a diode, right? So the circuit, when we look at it, the most commonly used form of the boost converter will have this form, where we have a VG, an inductor, and a switch which can be a transistor, and then here you have a diode with a capacitor and a resistor. And it is this presence of this diode which will cause this current to remain at 0 or enter into CCM mode, just like the case that we had in the case of buck converter. This is your VG, and here you will get the output voltage V0. Switch A, and this is switch B. Okay. So now we can label the time periods as we did in the previous case. So this duration is dTs, and this duration is d2ts, and here you have d3ts. Right? The condition is that d plus d2 plus d3 should be equal to 1. All right. So let us now apply volt-second balance and try to obtain the voltage gain for the boost converter. Okay, so again it is Vg times dTs plus Vg minus V0 times d2ts should be equal to 0. And as we have seen previously, Ts cancels out, and if you simplify this relation, then what you get is VO by Vg is equal to d by d plus d2. I think it is in the reverse way. Vg times d plus d2 will come, so it is d plus d2 divided by d2. Now again we run into the same problem, that even though we have now obtained a relation for the voltage gain, the parameter d2 is really not known to us. That means if we have a converter with certain values of L, R and switching frequency and duty ratio, everything else except d2 is known. d2 basically depends on how fast the current falls down, and so it is not really known to the person who has designed the converter at any operating point. So in order to simplify this relation and eliminate d2 from here, we can use the amp-second balance principle, just like how we have done for the buck converter case. So in most of these converters which we see, we will see a few more converters. The main philosophy of analysis remains the same. So you apply volt-second balance, get a relation, then use amp-second balance, get another relation, and then you can play around with them, substitute in different forms, and you can obtain the desired parameter or desired variable. So in this case, when we apply amp second balance, what we can say is that the average current through the capacitor must be 0. Therefore, the average current through this diode, this should be equal to the output current. That is something we have seen previously also, but this time it is in terms of D2. So if you look at the current through the diode, that will be equal to the current through the inductor. Only the difference is that it will have non-zero value only when B is conducting. So if I were to draw the current through the diode in this same figure, it would look something like this. It would follow this same waveform, but it would remain 0 during the on time, and only this portion would be present. And therefore, to calculate the average value of this diode current, the area that you need to look at is this shaded area, right? So the average value would then be equal to half into base, which is D2TS, into delta IL, that is the area, and therefore the average value would be this divided by TS, and this should be equal to the current through the capacitor, the current through the output, because the average current through the capacitor is 0, and therefore we can write this is equal to V0 by R. Right, so again TS would cancel out. Did I make a mistake? Half into D2TS times delta IL by TS should be equal to V0 by R. So yeah, this is fine, right? So what we then get is TS cancels out, so what we obtain is half into D2 TS into delta IL. So we can replace delta IL with the expression that we have derived. So delta IL is simply Vg by L times dTs, and this should be equal to V0 by R. So this Ts has cancelled out. So this is the relation that we obtain by simplification, and therefore again you can put this in terms of the conduction parameter K, because you have Q, L, R and Ts. So if you do that, we get Vg times D times D2 is equal to V0 into 2L by RTS, or this is simply K times V0. Right, so from this relation then we can say that D2 is equal to K times V0 by D times Vg. So why are we doing all these exercises? Because we want to simplify this voltage gain by eliminating D2 from this. So we are looking for a suitable expression for D2, which can be put in into the relation of VO by Vg to eliminate D2. Right, so let me call, so we'll call this as equation 1, and this would be equation 2, right? So if I do this and then substitute this value of d2 into the equation 1, so VO by VG was equal to d plus d2 by d2, so I can write this as 1 plus d by d2, and substituting for d2 from there, it gives me 1 plus d square Vg divided by k times V0, right? So I can write this as then 1 plus d square by k times Vg or Vo by Vg. Okay, so now I can again put this in the form of a quadratic expression. I have Vo by Vg in the denominator, so k times Vo by Vg the whole square, right? This is equal to d square plus k times V naught by Vg. So this is of the form k times x square minus k times x minus d square equal to 0, and so you can solve for x from here, or Vo by Vg would then be equal to minus b, which is k, plus minus square root of b square, which is k square, minus 4ac, which is 4d square times k divided by 2k. And if you cancel out k from the numerator and denominator, this would then give you 1 plus or minus square root of 1 plus 4d square by k divided by 2. Right, and 1 plus 4d square by k is always going to be greater than 1, and so its square root is also greater than 1. So if you take the minus sign, you will get a negative value, which is not compatible with the circuit that we know. So we can just omit this solution, and the final solution is then 1 plus square root of 1 plus 4d square by k divided by 2. Right, so that is the expression for the voltage gain in terms of all the converter parameters and duty ratio. Right, k is not like d2. Once you know the values of L, R and Ts, you can calculate k, and so you can straight away get the value of V naught by Vg. Right, so the point of this exercise was to look at how the voltage gain varies with the duty ratio in the discontinuous conduction mode. So the expression as such does not give much insight. So what we can do is try to plot this and look at the variation. So again, I have plotted this function using an online plotter. So let me just put the picture in here. So this is how the variation looks like. So on this axis, I have taken V naught by Vg, and here you have the duty ratio. And so the curve has been plotted with the value of k is equal to 0.01, that is this straight line, and this value is k is equal to 0.05, and here I have also plotted for k is equal to 4 divided by 27, which corresponds to the peak in the previous waveform which we have seen here. So this value is 4 divided by 27, right? So what we see is that the variation is almost a straight line for small values of k, and this is easily understandable from the expression that we derived as well, because if you look at this term inside the square root for very small values of k like 0.01 or 0.05, the term 4d square by k is going to be much greater than 1, and so 1 can be neglected with respect to that, so it can be approximately written as VO by VG can be approximately written as 1 plus square root of 4d square by k divided by 2. So if I can take the root, remove the root, then it becomes 2d by root k, 2d divided by root k, right? Or this can also be written as then half plus d by square root of k. So this then represents a linear variation, right? And therefore you see that for most part of the discontinuous conduction mode we have a linear variation of the voltage gain with respect to the duty ratio for continuous conduction mode for discontinuous conduction mode in the boost converter. And if you zoom this initial portion where the d is very small, you will be able to see, so this is not very clear from this figure, but you will be able to see this variation where the converter is initially operating in CCM, then goes to DCM, and then comes back to CCM, right? So that variation you will be able to see. So if the k is some value like 0.05, so then it will initially progress along the, so this curve which I have plotted, this curve is VO by VG equal to 1 by 1 minus d, which is the gain in the continuous conduction mode. And so if you operate with some value of k equal to 0.05, let's say, then the initial operation would be along this curve, right, along the curve for continuous conduction mode, and then at some point where the k value becomes smaller than the critical value of k, the operation will move along the discontinuous conduction mode line, right? And then at this point it again so happens that the output voltage will come back to continuous conduction mode and move along this line, right? And for the case of k equal to 4 by 27, it is just going to touch the curve of 1 by 1 minus d, and that happens at d equal to 1 by 3, and then the operation continues along the continuous conduction mode line. So that is the way the converter gain varies with duty ratio in the discontinuous conduction mode of operation. So with that we will conclude this discussion on the boost converter. Right? We will see some other converters in the next class. So